memory has become a very, very important uh, element in the whole system of computing. And if you can come up with a better memory, maybe you can achieve significantly better performance. So today we will start from basic, and then we will see how the memory is designed, how we can provide whatever data the processor is looking for. Because without that, even if you have a very fast processor, you can add all uh, pipelining and every other feature in your processor. But if the processor is not getting the data on which it has to work on, then all this performance, basically performance which your CPU has will not have any value. Now let's start from the very basic. Let's try to answer this question. Let's say I want to store some bits. Okay. So what is how can we store bits? Anyone? Registers. Okay.
By
Registers we
using
have already seen.
using
But
flip-flops, maybe.
how actually registers store the data? Okay. So it has flip-flops in it, right? Okay. So as we understand, if it is a, let's say, edge-triggered flip-flop, positive edge-triggered flip-flop, so whenever the positive edge of the clock comes, whatever was the value, that kind of the flip-flop memorizes and keeps it in the memory till the next pause edge of the clock comes. So that's why we call it a memory, right? So today, let's say I want to store a number which is 32-bit. So I can have 32 flip-flops to store those numbers. And if I continuously want to store this number and don't want any change, so every time the positive edge of the clock comes, I have to make sure that the data I want to store on those 32 flip-flops are same. So that's how I can store this. Now, anyone is aware of what is inside a flip-flop?
Yes.
Basically, how flip-flop stores this? Or, for example, we are saying that when the positive edge of the clock comes, the data, whatever it is, the flip-flop memorizes till the next pause edge of the clock comes. Okay. Achha. So someone mentioned about latch. So what is a latch? Uh-huh.
But instead of storing when it's an edge, it stores when enables on. You can read.
Okay, great. So it's very important because many companies will ask you this question: what is the difference between flip-flop and a latch? So flip-flop is an edge-triggered device, as we have already mentioned. Latch is a level-triggered device. As you mentioned that if enable or the clock is high, then whatever input is there, that will be available at the output. So whenever the clock is high, input is equal to output. Now, when clock goes down, then whatever was the last input till the clock went down, that will remain till the clock becomes again high. So I'll try to draw this. So we are discussing about a latch. So we will discuss about the simplest of latch, which is called D latch. So the input is called D, output is called Q, and this is your clock. Now what we have said? We have said that when the clock is high, so this is our clock signal. So let's say this is D. Now D is also changing, so we can draw some random wave. and so on. So this is the D. Yeah, so this is D, and let's say this is Q. Now, what is a latch? As we said, like whenever the clock is high, the level of the clock is high. So it's a positive level triggered latch. That could be negative level triggered latch. In that case, negative edge is basically the lower edge is the one which will make this enable. So whenever this clock is high, Q is same as D. Okay. So Q will look exactly like our D till the clock is high. Now at this point, clock went low. So at that point of time, D was low. So now, as if this is a switch, right? The switch remains on when the clock is high. And when the clock goes down, whatever was the previous or whatever was the input D, when the switch basically turned off, that value will remain at the output. So since when this clock went down, this input was low, so it will remain low. Even if the data changes here, this will not get reflected because my clock is low. Okay, so any change here will not get any effect. Now again, when this clock becomes high, then whatever is D, that will be my output. So this is a latch. Okay. So any idea how we can build this latch? So we have taken our DC course, right? And let's say I am giving you a 2 to 1 marks. All right. So you are given a 2 to 1 marks. I want this latch functionality from this 2 to 1 marks. I'll just make some connections. I gave you a chip which has a 2 to 1 marks. And I am giving you some wires and telling you that, okay, make some wiring and apply your input and clock, etc. in appropriate pins so that this 2 to 1 marks becomes a latch. Yes. Yeah, yeah. Yeah. So a 2 to 1 marks looks like this. It has two input, 0 and 1, and there is a select line. So if the select line is 0, then this input is basically this input is connected to output. And if this select line is 1, then this input is connected to the output. Now, see what we are trying to do. This is our D latch. So D latch is output is same as input when the clock is high. So when this is, let's say, clock, this clock is high, then I want my input to directly come out as output. Right? Now, when clock is low, so this marks will select this 0th input. So what do I want? I want the last output to remain as it is till this select line is 0. Right? So how can we achieve that? We can achieve that by connecting this output to this 0th input. Fine. Now, if you connect it like this and you are given a marks and you try this experiment, will it work? Hmm. No. So any input. So my input is this. Input could be 0, it could be 1. Whatever is it will come out as that. So basically the switch is on. It has to, because the last output will be now fed back as input. Right? So that's how till this clock is 0, I'll have the last output which I got from when the clock was high. Yes. So the question was, will this work if I connect it like this? And let's say the Q is currently 1 and then clock went low. Now, will it remain 1 till the next level, positive level comes?
Like the output goes to the zero वाला input, and we are assuming कि वो वहीं पे stay करेगा बाहर.
Mhm.
I don't know if it will stay at the like अगर हम when we are turning to zero, stay.
So basically, if you more practically, if you see like this, as if I have an output capacitor here. So if I am seeing 1 here, that means the capacitor is charged to high. Now, when my clock is 0, you see the capacitor is charged to high, but it has no other source connected to it. So it will not remain high. If you take a capacitor, charge it to some the highest voltage it can charge up to, and then remove the source, then what will happen? Gradually the charge will discharge, because these capacitors are not ideal capacitors. They will have some resistance across it, through which all of you are aware of the time constant, RC time constant, right? So through which the capacitor will discharge, and the time required to do basically for this discharge will be proportional to R and C values. So it will eventually discharge. So, but we want, it might happen my clock period is quite high. So I want this value to be remain high till the next positive level of the clock comes. So to achieve that, I have to introduce something here so that this capacitor remains charged. So what can I introduce here? Pardon? Diode will not be that helpful, because diode is again is not supplying any power. So what do you mean by a buffer?
I think it amplifies this.
हाँ.
वो चीज़ कैपेसिटर वाली जगह लगाते हैं. So like whenever it goes 1, so थोड़ा सा it will let the charge pass and it will store it to the it will keep flowing.
So some kind of refreshing circuit, right? So let's look at so you guys are all familiar with the gates, right? Your NAND gate, NOR gate, NOT gate. So if I connect two inverters here, so what will happen? So these two inverters, since doesn't matter. For simplicity, I'll change the direction, and let me just do this. Let's say I have these two inverters connected like this. Now, what are these inverters? So these inverters, whatever basically the input will get inverted, but since I have two inverters connected back to back, so the final logic will not be changed, it will remain same. But then how it will make sure that the capacitor does not get discharged? Because these inverters, do you know the internal structure of an inverter? CMOS inverters? Okay. So basically a CMOS inverter looks like this. It has two transistors. Sorry. So basically it has two transistors, one PMOS and one NMOS. This is ground, this is VDD. So this is your input and this is your output. So if your input is high, so let's say input is 1, at that time, NMOS, I'm sure all of you are familiar with the characteristics of an NMOS. You are applying a high voltage to the gate of an NMOS, so NMOS will be on. So your output is connected to ground, so that's why your output will be 0. At the same time, the PMOS, you are applying 1 in the gate, so PMOS will be turned off, so the VDD is not connected to output. So basically, this is complementary metal oxide semiconductor. So all these gates which are implemented in CMOS, they are implemented with a pull-up network and a pull-down network. Okay. So the pull-up network is here, your PMOS transistor. So if the PMOS is on, the output is pulled up to VDD. You will get a high output. And if your NMOS is on, your output is pulled down to ground, which is happening when you have a high input. Your output is pulled down to ground, and that's why you get a 0 output. So these are called complementary because both this pull up and pull down will not be on at the same time. Okay, so that's why your VDD and ground is never connected. So our power dissipation happens when VDD and ground are connected, so current flows. So that's why CMOS gives you so better power efficiency, because you are implementing all your logic without connecting your VDD with ground. So that's why there is no current flow. Ideally, there is basically switching current, etc. flows, but we are not going there. So now, let's say, and another advantage of CMOS is that, let's say this 1 is not exactly 1. It's, let's say, 0.8. Okay. Now, even 0.8 will make this PMOS on and make this inverter on, and it will, the output will be pulled down to a true 0. Because there is VDD and ground connected with your inverter. So even if your capacitor starts discharging and it gives a degraded 1 as an input to the first inverter, the output of this inverter will be a strong 0, because output is pulled down to exactly 0. And then this strong 0 will be again put as an input to the next inverter. So now when you have a 0 as input to this inverter, the PMOS turns on, NMOS is turned off. So your output is connected to VDD. So your output is pulled up to 1. So the next input to the mux. So at this point, you have a strong 1 as output from the second inverter. And this 1 is now connected to the capacitor. So the capacitor gets charged to true 1 again. So capacitor is trying to discharge. There is this feedback loop which is charging it again back to 1. And that's how you can keep this output level to 1 when this clock is low. Okay. Now, why I am discussing all these things? Because this is a latch, right? And if you have 2 such latches connected, then you get a flip-flop. So a master latch and a slave latch connected together gives you a flip-flop. So I'll not go into the details, but I'll just show you so this is a latch, and if you have another latch, I'm not quite sure let's see. This is a so this is a positive level triggered. So next one will be positive level or negative level trigger to make it a positive edge triggered flip-flop. I have to recheck, but you connect these two latches together and it results in, if required, I can show it in the next class. They will behave like a flip-flop. Now, why I am showing all these things? Because I wanted to give you a sense that how many transistor possibly you will need to make a resistor. Okay. So in the very simplest possible way, you can implement a mux like mux using transmission gate. So transmission gate is nothing but two transistors connected in parallel, one NMOS, one PMOS. And if I have two such transmission gates connected, then through this I can form a mux, 2-to-1 mux. So one mux needs 4 transistors. I need 2 inverters. So I'm just counting the minimum number of transistors which I need. So I'll need 4 transistors again for 2 inverters. So 4 plus 4, 8 for 1 latch. I will need 2 latches to make a resistor, make a flip-flop. So around 16. So you can optimize and you can make it with little less number of transistors. But you will need around more than 10 to 10, basically 12 to 16 transistors to make one flip-flop. Okay. And so storing 1 bit requires that many transistors. Okay. Now, is there a better way of storing 1 bit? We can store 1 bit like this as well. Yes. Okay, what is the question? Where we are? Oh, so each of these inverters are made of transistors. The mux is made of transistors, right? So basic building block of all your logic circuitry is transistors. So for example, this is one inverter. And the mux will have this kind of transistors, and basically a couple of them will form this. So I was trying to say that I can basically connect 2 inverters like this to store 1 bit. For example, let's say somehow I initialize this side with 1, then this output will be 0 and this 0 will be fed into this inverter, and this output will be 1. So I can see that I can store 1 bit using 2 inverters. Now I need little bit more circuitry to make sure that I can read and write this cell. If this cell is what I am going to use as a memory, I need some additional transistors to read and write this cell. So I'll have 2 more excess transistors connected to this back-to-back connected inverters. And using these excess transistors, I can read and write whatever is written inside this cell. Now, how many transistors do I need to implement this? 6, right? Because each inverter 2 transistors. So there are 4 transistors and 2 excess transistors. So that is 6 transistors. And we'll call this 60 SRAM. So SRAM stands for static random access memory. Pardon?
How
So each of these inverters, they need two transistors, one PMOS, one NMOS. So this is an inverter. This is input and this is output. Okay. So you have two such inverters. So 4 transistors, 5 and 6. Okay.
Capacitor. We attach a single capacitor. If the delay is long enough, we'll store it and it will fully charge it, and then it will, when it will flip, it will stay.
Okay, I'll come back to this. So this is called static random access memory. Anybody can help me understand why static, random? So what are these terms? Why are these terms there?
We can't change it. I think it is called static because there's no current flow.
Okay, yeah, partially you are correct. So there is no dynamism. If, as you are mentioning, if I had used a capacitor, so capacitor is dynamic. So I charge it, it starts discharging. So I'll show you the other alternative to this is DRAM, dynamic random access memory. So DRAM uses a capacitor to store the bit. But let's focus on this. So this is 6 transistors. So that's why it's called 6T, static random access memory. Static because there is nothing changing, no current flow happening when you're basically you are not trying to read or write this cell. And random access. So if I build a memory using this kind of cells, I can randomly access any bit in that memory. I don't have to go sequentially. It's not like a tape. If I had a tape for storing data, then I can't randomly access a far end of the tape. I have to go sequentially. But here, I can randomly go to this particular location and read this bit. For reading and writing, I have to, basically, I'm not going into the details. So basically, there are 2 wires called bit and bit bar. I have to initialize them if I want to read, write something, depending on what I want to write. And then there is a word line select signal, which selects, basically, which keeps this access transistors on. So randomly, anywhere, if I have a memory built with this 60 SRAMs. All your cache memory is built with 60 SRAM. All right. In our computers, mobiles, almost everywhere you will find 60 SRAM is used for implementing your cache. All levels of cache, L1, L2, L3. Okay. Now we looked at resistors. Resistors or flip-flops, we saw that requires more number of transistors compared to this. But the advantage of these flip-flops or resistors built with flip-flops is that they are faster than SRAM. Reading and writing a flip-flop or a resistor is faster compared to SRAM. But they are more expensive because I need more transistors, the density will be low. So if I want to store 1 GB of data, and if I use these resistors, then I'll need huge amount of area because compared to SRAM, it will take at least twice or thrice the amount of area to store the same amount of data. So we have seen 2 types, resistors or flip-flops and this 60 SRAM. The other one, which again, all of you are you might have used this term also, DRAM, or typically we call it RAM. The RAM in your machines, whether desktop or laptop, even your mobile phones, So they are typically the DRAMs. So most of the times nowadays we use 8 GB at least as our RAM, right? We look at the specification and we say that, okay, I need at least 8 GB RAM. Now, 8 GB of memory, if you want to build using 60 SRAM, again, it will be very, very expensive. Okay, so that's why you don't want to use 60 SRAM or resistors for implementing that 8 GB RAM. Rather, you would like to use something more which can provide density. So the DRAM is a very simple way of storing a bit. So you have a transistor, and this transistor is connected to a capacitor. So this is your word line. So basically, the row you want to select to read or write, you will be selecting it by enabling this word line. And then there is this line, which is basically your bit line, which depending on what you want to do, you want to write something. For example, you want to write a 1 in this. So what you will do, you will make this bit line 1. You will enable this word line. So what will happen? This is an NMOS. So this gate is connected to a high voltage. So this switch is on. Now, if you connect 1 here, the capacitor will get charged to 1. So that's how you store 1 in this cell. Similarly, you can store a 0 in this cell by initializing your bit line with 0. Similarly, you can read by basically not initializing this, by observing like when this word line is on, how this bit line value changes. So if it is storing a 1, then this bit line value will have a small potential which you can detect and say that, okay, I have a 1 stored in there. So this is your DRAM, dynamic random access memory. Okay. So here you need actually 1 transistor to store this 1 bit. So the density is really good. That's why you can have 8 GB of DRAM at a reasonable cost, right? Now this is very dense because only 1 transistor is required. But the disadvantage is it is quite slow for reading and writing. The other challenge is this capacitor, by virtue of the fact that it's a capacitor, it will be discharging. So you need to have an elaborate refresh circuit. And you have to refresh your DRAM very, very frequently. I think the standard these days are 60 milliseconds or so. So every 60 milliseconds, you have to refresh your DRAM, the content of what is stored in this DRAM. Okay, so these are the 3 different ways typically our memories are implemented. We will not go beyond that because then there is hard drive and all these things which are much slower compared to what we have. Yeah, it's word line enabler. So basically, I'll give you a idea about it. So let's say I want 32 kilobytes of memory. Okay. Now let's say my word size is 32. So what I decide is that okay, I will store 1 word in 1 row. That means 32 bits I'll store in 1 row. And since I have I want 32 kilobyte, that means what? I'll have 1,000 rows, 1,000 such rows, right? So if you really proportionately draw this, it will look like a very skinny, tall structure, right? Because it has 1,000 rows and each row is 32 bit wide. Now, to read or write anything in this memory, what I'll do, I will have a row decoder circuitry, which will enable the row which I want to read. Now this row will be enabled by this word line signal, which if I make high, that means now I can read or write this particular row. Okay, so this word line signal is nothing but this signal. It is connected to 32 such transistors. Each of these 32 transistors will have their bit line, and I will initialize those bit lines, and accordingly I will read or write. Similarly, here if it is a SRAM, then I'll basically this row word line select will select that particular cell. Okay, so using this word line signal, I can select the row. Now here you see that if I build my memory like this, then do you see any issue here? So basically 32 kilobyte of memory, I have put one word in each row, and I have a long, basically very skewed, skinny structure as my memory. So this has several issues, basically your floor plan, because ultimately these transistors will be fabricated on a silicon substrate. So your floor plan will look bad. Also, think about the length of the wires. So your row decoder circuitry will be somewhere here. Now row decoder means that I have some logic, and the logic will tell me which row to be enabled, because I need to read and write different rows. So now this row decoder will be connecting to all these different rows using long wires. Now the biggest enemy of achieving performance in a compact circuitry is these long wires, because we are making transistors faster and faster by shrinking them, etc. But the wires are not shrinking. And as you have a long wire, the wire behaves like a transmission line. So it has capacitance, inductance, and resistance. And because of which the delay provided by this wire will be significantly high. So you really don't want to make this kind of a skewed memory structure. So rather what you want is basically you want multiple words to be there in the same row. Okay. So this is fine. But another problem is now, along with your row decoder, you need a column decoder also. Because you want to read a particular word, then you have to tell that, oh, it's in this row, this column, right? But still, that is a reasonably good problem to solve by making this memory structure rectangle or square. We are basically making sure our wires are not too long, and we can build this memory in an efficient manner. Okay. Abhay Kumar, please mute yourself. So, so basically this this way we have we can build our memory, which is more balanced. The wires, etc., are not too long, etc. Okay, but we need, along with our row decoder, we need now column decoder also. So if we summarize the memory technology which we have discussed so far, so we talked about SRAM, DRAM, and the latches or resistors. Then as a summary, we can say that so if, let's say, in one end we have low capacity and low latency, And basically I can read and write very quickly. So that means high bandwidth. On the other end, if I have, let's say, high capacity, high latency, and low bandwidth. So among the three memories we have mentioned, which one will go where? So at one end we have high capacity, high latency, low bandwidth. Which one will fit this? DRAM, right? DRAM has high capacity, but latency is high. Also, the read-write speed is not as high as, let's say, our SRAM or latches and resistors. So low capacity, low latency, high bandwidth. So basically our resistors, requires lot more transistors to implement. That's why I can't have too big memory, so low capacity. It has very fast performance, basically low latency, and it can be read and written very quickly. That's why high bandwidth. And this is DRAM. SRAM sits somewhere in between. Okay, and because of that, basically you see the memory hierarchy which your processors or your computers have. It has same hierarchy. So the closest thing to CPU is your registers, your general purpose registers, where you want to put all your variables which the CPU can directly access, etc. It has low capacity but very high speed. So if the CPU is working at a, let's say, 2 gigahertz clock, then I can read and write at the same clock from the registers. So high bandwidth also supports that I can read how many registers I want to read. I can read it at that time. The DRAM, on the other hand, you remember that we said that the ISA decides that how much memory the processor can handle. So that is determined by the number of bits you are reserving for your address space. So typically, let's say 32-bit address space, if you have if you are using in an ISA, that means you can access 2 to the power 32 different addresses, which is 4 GB, right? Now, so any processor you want to design and want to get the performance out of it, the programmer will assume that the programmer has all of its memory. That means 4 GB, because the programmer, while writing a program, he doesn't care that what else is running on that computer, right? So they will assume that, oh, I have all my 2 to the power 32 memory spaces, and it will he or she will write the program like assuming that. So that means as a hardware designer, you have to ensure that you give that much memory, because if the program is trying to access some memory location which you have not defined, that means then the program will crash, right? So now that means I need to provide this much high capacity of memory. Even for a 32 address space, I need 4 GB memory to be provided. So that's why we will use the high capacity DRAM to provide that. So this is called main memory, right? So in your CPU design or CPU initial discussion, we said that this is your CPU, this is your main memory. So the DRAM is nothing but your main memory. Okay. So it doesn't matter whether you have a terabyte hard drive or not. Your terabyte hard drive is not directly getting accessed by the CPU. The CPU will only access till the main memory. So CPU is oblivious of how you have implemented memory. So processor will request for data and it will give the address that, okay, get the data from this particular address. It will give a 32-bit number, 32-bit address. You have to figure out that where this address goes to, basically where it is located, fetch the data. Now, since 32-bit address, so that means theoretically it can give anywhere from the 4 GB address space. Yeah.
CPU or the processor in the Xbox
Hmm.
gets direct access from the SSD. Has direct storage.
Mm-hmm. So there is basically there is not only Microsoft, even there are other companies like IBM, I think first did that. So it's a basically the basic concept remains same. So you expose your address space to the SSD. So that's how yeah, it's little complicated. I'll maybe maybe we can discuss this offline because the way you access your memory has several steps in it. So it's not the processor, what is it is asking for is directly getting, you are getting it from the hardware. There are some translation in between, which helps you to get the, basically manage the memory better. If time permits, I'll talk about some part of it. But yeah, let's fix this for now, that CPU requests data from memory. Now, the basic problem is that memory is slow because we are talking about our main memory of, let's say, 4 GB, or if it is a 64-bit address space, then it becomes like 2 to the power 64 address space, right? Even bigger memory. So now, how do I provide the data which the processor is looking for at a reasonably good speed? Yes.
The DRAM to SRAM is handled by the processor itself or in the assembly?
No, it is none of them. I'll talk about it. So right now, we don't know that there is these 3 levels, etc. Right? We just said that, okay, there are registers and then there are memories. So we will load, store data from memory. Now we are saying that, okay, memory can be implemented using SRAM and DRAM. We will see where SRAM will come. For now, let's assume that we are only aware of that there is DRAM, which is implementing this 4 GB of memory, which we need, the processor needs. Okay. So the takeaway I want to highlight here is that DRAM provides you high capacity, latency is high, but to accommodate lot of data, DRAM is the solution which is used, because you need only one cell to store 1 bit. So now so this is our CPU, and this is our main memory. The CPU also inside has this registers, general purpose registers. So every time we encounter a load or store, we need to go to the main memory and update that data. So you remember in our microarchitecture, we had this data, basically data memory and instruction memory. Okay, so we are talking about this memory. Okay, now the challenge with this memory is that we said that, okay, we want to have sufficiently large memory so that we can accommodate all the data we need while we are working on a program. So to have that amount of memory, or to basically accommodate everything in the data memory, our data memory has to be large enough. So let's say I want to multiply 2 matrices, which has, let's say, each of them has 1 million entries. Okay, So 1 million multiplied by 1 million. So that kind of matrix I want to evaluate. I am designing a processor to do this task. Now, how do I store these two matrices which I need to multiply in the memory? So I need a memory of that big size which can accommodate these two matrices, each having 1 million elements, right? So now, what we are trying to highlight here is that to accommodate the data which we are dealing with, we need a reasonably large memory. And we said that, okay, if you want large memory because of the capacity, etc., DRAM is the choice to have. But DRAM is slow, and it becomes even slower when you make it very large. For example, if you have 4 GB of DRAM, there is a physical dimension associated with it. The larger amount of bits you want to store, the physically you need more space. Now, as your physical space becomes larger and larger, the wires which are connecting these different cells. So each cell, okay, so basically each cell will be connected with these wires because you are asking for large memory. Now in digital circuits, or for that matter, any circuit, let's say I ask you that, okay, I give you an inverter and ask you to find out what is the delay of this inverter. So how do we calculate delay? We say that, okay, if input changes at this particular time, at what moment the output changes. So after certain delay, the output will change. So you measure the delay, right? Is this fine? So I have an inverter and I'm trying to find out what is the delay provided by this inverter. So when input changes, after how much time the output changes. Now for this kind of, or for that matter, any gate, the delay is a function of what this inverter connected to. For example, is this inverter driving another inverter? Then the delay will be certain value. If I say that this inverter is driving 3 such inverters, then the delay will be more or less. Any guess? So let's say earlier this inverter was driving 1 inverter only. So it gave me 1 nanosecond delay. I'm just exaggerating. Now it is driving 3 inverters.
There are 3 outputs, so each of the output have the same.
So I am only asking you that what is the delay of this inverter? So someone said same. Anybody else has any other opinion? Pardon? Inverters are in parallel, the output. They will have. So I'm interested in the delay provided by the inverter which is driving these 3 inverters. So earlier it was driving 1 inverter, now it is driving 3 inverters. So when an inverter is driving 1 inverter, so if you look at the electrical or the current wise, what is happening? So it has a load capacitance. So this inverter is essentially basically driving this load capacitance. So the delay, so delay is what? So you made some input change. Because of that, the output will have a change. Now output is changing because let's say this is what the inside of this inverter looks like. So when this NMOS turned on, so you have to discharge this output capacitance to make the output 0. Now when you have only 1 inverter connected here, the capacitance, basically each inverter connected has an input capacitance. So the amount of capacitance that this inverter has to discharge will be small compared to when you have, let's say, 4 or 3 inverters connected. So it will be driving more load. Okay, so it's like you are pushing one carton and somebody put 2 more cartons on top of it. So earlier you could push at a certain speed, now your speed will be reduced. So the point I want to make here is that this is called fan out. Okay. So when in electronic circuits we mention delay, it's always dependent on what this circuit is driving. If you don't mention that, then this delay has no meaning. Okay, so you can say that, oh, I have designed a NAND gate which has this delay. But then immediately the evaluator will ask you, what was your fan out? What is fan out? Fan out means how you have calculated the delay, how many other elements it was driving. So a standard delay measure is called fan out of 4, FO4. FO4 delay is a very standard term in so every time you want to report some delay, you have to report this FO4 delay. So what is this FO4? FO4 delay says that if I am reporting the delay of an inverter, so I report the delay of this inverter driving 4 such same inverters. So this is my FO4 delay. So this inverter driving exactly same such 4 inverters, what is the delay? So this is called FO4 delay. Now, why I am discussing this here? Because if you have a big memory, you will have lot of wires which need to be driven by the different circuits. For example, the decoder circuit. If you have a big memory, maybe you have to drive hundreds of wires because there are hundreds of rows. If you have a small memory, maybe you will have 10 rows. So when you are driving hundreds of rows, then your delay will be more compared to when you are driving 10 rows. So as you make your memory big and big, the memory becomes slower. The wire lengths become slower, the delays become larger. That's why you can have a big memory, but you can't read or write it very quickly. On the other hand, we said that, okay, we need large enough memory, otherwise how will do this big matrix manipulations? For example, I want to do image processing. So I have 4K frames coming at a speed of, let's say, 30 or 60 frames per second. If I don't have memory, how I'll store them? And because my processor can't do anything without storing. So I have to store the data in data memory, and then I have to fetch it, work on it, and so on. So these are two contradictory requirements. We need large memory to run our programs, but we can't make them fast. So this is the challenge we have. And this challenge is called CPU or processor memory bottleneck. Yes.
Current memories are so like a small piece of like when we insert it, it only takes a small input. Wouldn't it be much more efficient if it takes the whole surface area as input to be exact as input? Like if it has five pins coming out of it and square.
So are you talking about the USB drives, etc.? Or
Any
so if you see your RAM is connected through PCI, it goes into the PCI slot. So PCI is one of the standard, quite fast interfaces. So basically those interfaces, etc., are already fast. Yeah. So this diagram, again, it's from the standard Hennessy-Peterson book of computer architecture. It shows that how processor speed and the memory has changed. So memory has not become as fast as we wanted compared to processor. So this is a logarithmic scale. So you see the performance of processor has really improved exponentially, and memory has not improved that at that pace. So it is compared with a superscalar processor. So the microarchitecture we saw, it is a scalar processor. So it can only take one instruction and then execute it, etc. So if you have a high performance superscalar where multiple instructions can be taken, so it can actually take 4 instructions and running at 2 gigahertz speed. So by the time it can access a DRAM, it could execute 800 instructions. So you see that the mismatch of performance. So if your data is in DRAM, the processor will wait the amount of time by which it could have executed 800 instructions. So you see that though you have very high performance processor, because the memory is not giving you the data you need, you will not be able to achieve the performance. So we have to somehow address this issue. So one possible way and one smart way to handle it is basically this observation that, okay, if I have a small memory, I can access it in reasonable time. But if I have a big memory, the access time becomes very, very high. So that's basically the reasons are mentioned here. Signals have to travel further. As I said, like the wire length will become longer. The fan out, you have to go to different locations. So that's why the fan out will increase, and that's why the delay will increase. Now the hack to this, or the way to tackle this problem would be, can we have something which also inspired us to add resistors in a bigger scale? So the idea is that, okay, you have this big slow memory, but in between, can I put a small fast memory and hope that most of the time what the processor requests, I can serve it from this small fast memory. And this is what is called cache. And we will implement this cache using SRAM, because the performance is intermediate, and we can basically, it's not as expensive as, let's say, your resistors, etc., but it's performance wise is much better than the DRAM. So capacity wise, resistors are much smaller SRAM compared to SRAM, and it is even SRAMs are much smaller compared to DRAM. Latency wise, resistors have the best latency, followed by SRAM, followed by DRAM. And so as long as you are on chip, so anything you are doing inside the chip is much, much efficient compared to going off chip. So off chip means you are trying to access data from, let's say, your DRAM, or you are going to your hard drive, that is much more slower. Yeah. So bandwidth is basically the, so okay, bandwidth is basically the amount of data you can transfer at a unit time. Okay, so it's basically the a very crude example could be the width of the road. Let's say it's a 4-lane road or a single lane road. Now in each lane, at what pace the data will move or the car will move, that is your latency. Okay, so basically, if I have a highway where the speed limit is 120, then the latency will be small. Okay, compared to a road where the speed limit is, let's say, 30. Yes.
Single register once per cycle. How is that? How do you capture select?
No, so that actually you can read, write simultaneously. You can read multiple registers also based on basically how you want to design your register file. So, for example, in the register file, what we have seen, you see that we can do read and write in two successive basically edges of the clock, right? So that means it is capable of doing things very, very quickly and with efficiency, right? So similarly, bandwidth is not that big an issue in registers, because anyway you are storing very limited amount of data. So even if you have to transfer all the thing which you need to which you have stored in your registers, that will not take much time. If you have to transfer 4 GB of data, then bandwidth matters, like at what rate you can transfer the data. So for example, let's say I want to copy the whole DRAM content to a hard drive. So bandwidth will decide how much time it will take. Now, if I want to read or write a particular byte or word in the DRAM, that is latency. Okay. Yes. So chip is the die area, silicon. Basically, for example, in your, if you open your laptop or desktop, you will see that there is a processor chip, right? And your RAM is outside. These are basically connected on slots, right? So whatever is inside this chip, moving or interacting among them is much faster.
DRAM is out of.
DRAM is outside the chip. Your caches are inside the chip. Cache is the SRAM.
Why do we see the register based memories?
Just
Processor and RAM is separately.
so basically, if inside the chip, whatever is there, it is on chip. Now, whenever you go outside the chip, you go through these pins which are there, right? So the pins have lot of inductance, capacitance, and that results in huge amount of delay. That's why anything you need to do off chip, it is, let's say, tens or thousand order of magnitude higher compared to what you can do inside the chip. So your question was why we don't use registers to build memory? Yeah, because that will be hugely expensive.
But like if my purpose is solely like I want to play games and I have infinite money, so didn't a register based big memory make sense? Because currently I don't know where is it.
Because the cost and the benefit you get compared to SRAM is not sensible. So basically, most of the computer architecture related design decisions are based on some trade-off. You can add more resources, more money to get certain percentage improvement in performance, but you also see that what is the percentage improvement. Like if I spend 10x more for getting, let's say, 1% improvement, that might not be viable.
Register based
So it's not directly register based memory. Basically you can improve or you can make your caches, the architectures of the memory much more efficient. So all these things are done. Even in some cases, maybe you want your first level cache, instead of SRAM based, you make it, let's say, register based, or SRAM with some tweak in it so that it performs even faster. Okay. Now the catch here is that we are fine to have this kind of tweak of having a small fast memory in between, But here it will only work if most of the request from the processor can be served by this small fast memory, right? Even let's say I have this small fast cache in my processor, but most of the requests are getting served by the main memory. Then what will happen? So you send the request, you check it in the cache, and you found that, oh, the data is not there. You go to the main memory. So your delay to access the data even increases, because there is one additional delay of checking it in your cache. So this will be only beneficial if this small fast memory can actually store data that is reused by the, or that is used by the processor. Now, luckily, if we look at the access pattern of data by the processor, there are certain trends which can be easily observed. For example, instruction memory. So instruction, typically we fetch one after another, PC plus 4, right? So PC, then PC plus 4, PC plus 4, and so on. So sequentially accessed. So I can guess what to store in that small fast memory so that I can provide provide the CPU what it wants. So I can prefetch, or I can store it in my cache. So typically instruction fetches has this pattern. So I access a particular address, then the next address, then the next address, then the next address. And then if there is a loop, then I'll go back to some previous instruction again, and so on. So there is an access pattern. When we are writing functions or subroutines, so there is also a very standard access pattern. So you will be basically pushing all your data to your stack. So push, 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 then work on some variables, and then again pop all this data, and so on. So again, there is a access pattern. Okay. Data access pattern is also most of the time very much predictable. For example, if you are reading an array of numbers, so if it is a vector, then this is how the access pattern will look like. This address space, then the next address space, next address space, and so on. If you are accessing the same data multiple times, then also this is how the access pattern looks like. Now, if we observe this access pattern, so there is something called temporal locality and spatial locality. So what does that mean? It means that if a location is referenced once, it is likely to be referenced again in near future. So basically, if I have used a particular data at this particular time, it's very likely that at some time in near future, I'll access the data again. So that is called temporal locality. Spatial locality, if a location is referenced once or referenced, it is likely that the locations which are nearby, they will be also accessed in near future. So for example, if you are trying to access a particular element of an array, instead of only bringing that particular element from the main memory, you bring the adjacent elements also, hoping that your processor will request for the other elements also from that array. So this is called spatial and temporal locality, and using this spatial and temporal locality, we will try to populate our cache in such a way so that most of the time the processor gets the data from cache what it wants. And this is not only theoretical observation. So again, this is taken from this IBM System Journal. It shows the actual memory access pattern for a real processor. And these are memory addresses, and each dot represents one memory access. So you can see temporal and spatial locality in several parts of this access pattern. Okay, so So basically cache exploits both this type of localities. It exploits temporal locality by remembering the content of the recently accessed location. So if you access a particular location, you do not remove it from the cache for a certain amount of time. So let's say you are accessing a particular variable, so you bring it in your cache and you keep it there for certain amount of time, hoping that the processor might want to reuse it. So that's temporal locality. Spatial locality. So by fetching, instead of fetching a particular word, you might want to fetch the adjacent words also. So exploit spatial locality by fetching blocks of data around the recently accessed location. So that's how you can um, populate your cache. And we will, in our subsequent 2 lectures, we will talk about how this cache is classified based on how we populate this cache, how we evict data from cache, how we access data in this cache, and so on. All right. So before we close, let's have this quick class interaction. So if you are done, we'll stop here today and we will resume from here in the next class. So we have 2 more classes after that. And we'll try to cover as much memory as possible. If possible, we'll also talk about virtual memory. Okay.